Hey, welcome back everybody. R.4, we are talking about something called angular motion. After tackling the idea of torque, the cousin of force, now it's actually time for us to almost start way back from the beginning, the very first set of videos looking at motion. Now we're not going to be looking at motion moving in translational types of ways, but we're going to be looking at motion that's angular or rotational. To be honest, it's called angular more often, and you'll see why in a second, but you could just as easily call this rotational motion. You'll probably hear me use the two interchangeably. You could use the two terms interchangeably, but angular motion or rotational motion, okay? Now, to start off, the first bullet point I have right there, it says we need a way to measure the rate solid objects rotate that makes sense. And that's certainly implying that up till now, what we've been using doesn't really work. And here's what I mean. When we were studying motion, and heck, even forces and momentum, obviously all of our definitions, our equations, they were all for translation, an object moving from one spot to a different location, a different coordinate location. We now know that's different from an object rotating, and as you'll see right now, it doesn't help us to understand things that are moving by using those same translational kind of set of coordinates or set of equations. Here's what I mean. I have right here a little simulation, and I have this rotating platform where it looks like there's a ladybug and a green beetle, okay? They're moving around and around, and we saw when we were doing circular motion that the ladybug, oh, there's that green, has some velocity that's tangent. The beetle has some velocity that's tangent. If you notice, if you look real close, especially if I pause it, you can see, oh, there's the centripetal accelerations of the two things. And also maybe you recognize, oh, the beetle has more tangential velocity, right? Because it's traveling a greater circumference in the same amount of time. That's all well and good. Except now, in this rotation unit, we don't really care about the beetle or the ladybug anymore. Now we care about the platform, right? This unit is focusing on the thing that's rotating. Well, what's the problem? What do you see if I was trying to look at the speed of this rotating platform? Well, depending on where you are on this platform, it could have a different speed, right? This ladybug, this distance r away, has a different speed for this rotating platform than if I was the distance of the beetle. So depending on where you are on this platform, that platform has different speed. And that's weird, and that makes it, least of all, impossible to really apply forces or torques, because we'd always have to decide where our radius is, and what if the radius is changing, or what if we then started looking at a different distance away. The old version of tangential velocity, regular old acceleration and force, it doesn't work anymore. So we need another way. And what is that other way? I'm going to slide this over just a little bit. Well, if I instead focus on the angle, hence why it's called angular motion. So right here, obviously the ladybug and the beetle, they're on kind of the same line. They have different velocities from the normal sense, but if we think of this, okay, well, in one moment they're here, and the next moment, oh, they're there. Then another moment, and another, and another. Because they're on this line, this angle that they're making, that is staying constant. The kind of linear distances, well, that's different, and therefore their linear velocities are changing. But because they're making the same rotation in the same chunk of time, and the angle is therefore staying the same, we can look at the change in angle. And that's the idea. Of course, that's why it's called angular motion, okay? So let's get started really officially with our notes, okay? Here's a diagram that I do recommend you draw. We need a new way to measure the motion of an object for something that's rotating. And we're going to do that using angles. So how will we do that? Here I have a bicycle wheel, but very similar to the diagram that I just showed you, okay? We often start measuring along this x-axis. Remember how you can start measuring like your x equals 0 spot wherever you want? Well, the same thing is true. But traditionally, we will measure the starting angular location from this x-axis. So oftentimes this spot right here we'll just call theta equals 0. And that's our initial spot, so theta naught. Just like we would often say x naught equals 0. Well, if that bicycle is rotating, some amount of time later, now it's at this location, some angle right here. Well, that's my final position. So what is my angular, displacement? My delta theta? Well, that's just going to be theta minus theta naught. just like my change in translational displacement was x minus x naught. Remember how I talked about cousins? Now we have this cousin. For things that are rotating, we're going to look at displacement, yes, but now angular displacement. And then we're going to build off of that, okay? So let's get started. I have a part A, B, and C, but it's going to go faster as we go. In fact, this part A is the longest chunk of all the others, but I do recommend you write this down, okay? Part A, angular position. What I have right here is kind of a solid, almost formal definition. It means it's actually a little bit confusing, but an angular position, it's an angle between a reference line, which again is usually this x-axis right here, and a line drawn from the axis to the location of the object. What the heck does that mean? Well, imagine I have that coin on my rotating turntable again, okay? If the coin is now sometime later right here, well, the angle is the measurement from the line, starting from the axis to where the object is, and it's to that origin, where we normally say right here, theta equals 0. So my change in position, well, it's whatever this angle is. So delta theta equals theta minus theta naught. We'll usually call this right here as 0. I don't know, maybe this is 50 degrees, something like that. So the angular position, the angular displacement, well, it changed by 50 degrees, or it started at an angle of 0, and it ended up at an angle of 50 degrees beyond that, okay? Delta theta, the angular displacement, is the change in angular position, okay? Now, we are using radians because classically, physics for rotating and angular motion, it uses radians. You could use degrees, but what's most common is radians, and therefore that's what we're going to use. First, don't worry. We're not doing any trigonometry with radians, which means you will never have to change your calculator from degree mode into radian mode. So just keep it in degrees, that's fine. While we're going to be using radians, there's not going to be any trig using radians. But what is a radian? Because it's a little different. A radian is defined as the angle subtended, kind of the angle that's created by some arc, S. And what is S? S is kind of like a distance. But it's this arc length. It's this curve going from one spot to another spot. Notice it's a curve, right? Because it has some constant radius r away, so it's going to trace out this kind of curve, whose length, this S here, equals the radius itself. Oh, yuck, kind of weird. I'm never going to ask you to define this right here, but it's going to be important that you recognize that we will be using radians in this class as a way to measure angle, as a way to measure angular position, and a way to measure angular displacement, okay? For example, 360 degrees, one complete circle, well, that's equal to 2 pi radians. Radians doesn't have any units, it's just 2 pi. Okay? You don't need to know where this comes from if you're rusty on your unit circle, but one complete revolution is 2 pi. 180 degrees, half a revolution, well, of course, that would be pi. If something changed or something arced 90 degrees from here to here, well, that would just be pi over 2. These might be helpful. I would maybe recommend you write this down. Again, not that I expect you to have to derive it, but you might see in a problem, you know, a ladybug travels along a platform for half a revolution. If you're doing some angular velocity or angular motion calculations, which we're about to get to, you need to know, hopefully, just at the top of your head, what those are in terms of radians, okay? So that's angular position. Just like regular old position, okay, it's where you're located from some reference point, but now it's an angle, all right? Well, now we're going to move a little faster, okay? Average angular velocity. So just like before, we learned about displacement and then velocity and then acceleration. Let's do that for rotational or angular motion. So the average angular velocity. There's a new symbol that we haven't seen before. This is lowercase Greek letter omega. Don't say W, it's obnoxious. This is Greek letter omega. Uppercase omega, you might be more familiar with. It looks like that horseshoe. That's uppercase omega. This is lowercase Greek letter omega. Well, what was velocity before? It was the change in position or the displacement divided by time. It's the same thing. But for angular motion, it's the change in angular position or angular displacement divided by t. What is the units of this lowercase Greek letter omega? What is the unit of angular velocity? Well, it's the unit of the equation. That's radians per second. So if there was a problem and it said, I don't know, you have a wheel and it rotates 180 degrees, or it rotates pi radians. It rotates pi radians in, I don't know, 3 seconds. What's the angular velocity? Well, it's delta theta divided by t. That would be pi over 3 seconds. Plug that into your calculator. You get a decimal, right? Something a little bigger than 1. And that would be something in rads per second, radians per second. That's it, angular velocity. It's just like our regular one, displacement over time, but now it's angular displacement. That's my cousin. Let's keep going. Just like we had acceleration is the change in velocity divided by time, there's an angular acceleration. Angular acceleration is the change in angular velocity. That would be omega minus omega naught divided by t. That would be the units. Well, the units would be radians per second divided by seconds. Okay, radians per second divided by seconds. Or you could call that radians per second squared. Just like regular acceleration was meters per second squared. Okay, next one. Well, now that we have a basic idea between angular displacement and velocity and acceleration, what do they look like? They look like what we learned before. Remember, cousins. These are the cousins. Here's regular old velocity. Here's angular velocity. Here's regular acceleration. Here's angular acceleration. They're just cousins of one another. Okay? Displacement over time. Still displacement over time. Still change in velocity over time. Just now, it's the change in angular position. The change in angular velocity. But very similar kind of physics. Okay? Now, it turns out you can actually go from one version, angular motion, to our original translational motion. Let's see how to do that. Our regular equation for velocity, and I'm going to put tangential just to imply that that's that linear version. Okay, we know that that's just distance divided by time, right? Distance divided by time. Well, if I look again at this coin on the platform, what's the distance it travels? Remember, it's this arc length, this thing that they call s. So that's s divided by t. Or technically what I just drew in, it's the change, right? It's the change in position divided by the change in time. Okay. But I actually now already have another equation that involves this arc length. Now that doesn't seem particularly helpful, except we've already seen an equation for s. We learned that theta is equal to s divided by r. That was our definition of a radian. Or, the change in theta, that's the change in arc length divided by r. So that means that delta s is equal to r times delta theta. I could plug that in right there, and I'm left with that tangential velocity, kind of the regular old velocity, that's equal to r delta theta divided by t. What is delta theta divided by t? Oh, that's that angular velocity. So look right here. Well, this is not, to be fair, on the AP equation sheet, and you're probably not going to be asked to do a direct translation. You can pretty easily go from linear velocity, translational velocity, to angular velocity with this equation. And you actually have something very similar for acceleration. Linear or tangential acceleration, that's r times the angular acceleration. In my class, you might see a homework problem or two. If you're in a college class, these might be helpful. Okay? Not super often on the AP exam, but it was actually pretty easy to derive, to come across. Okay? The last thing, oh my gosh. If you have constant acceleration, we learned 3 equations that dictate the motion of objects when there's a constant acceleration. Well, I can have something rotating with a constant acceleration. And once again, I have cousins. I would absolutely copy this down. I might recommend you copy both down just so you clearly see that they're cousins. But at the very least, these 3 equations, which are on the AP equation sheet, you might be asked to do a calculation with these equations. But notice, they're the exact same thing. Velocity is initial velocity plus acceleration times time. Angular velocity is initial velocity plus acceleration times time. All 3 of these are more or less identical looking, just they are using their angular cousins. And of course, we'll get a lot of practice with this. A little weird at first, kind of, using these new and different symbols, but it's the same physics. It's still the idea of looking at motion. Is something speeding up or slowing down or a constant velocity and applying the applicable equation in order to solve. Okay? Man, that's it. I'm done talking. Thanks a lot for watching.